Yeah, polar orbit. Yeah, polar orbit. It's usually we will see that it's inclination of degrees. That's reference to the equator. That should be as a 90 degrees, and depend on the moment and how they will be passed through the orbit. It's different paths are having different ways. It is around about 100 to 600 kilometers from the equator. Then geosynchronous and geostationary orbits. These are geosynchronous and geostationary orbits, which is reference to the satellite, and it's maintaining the same angular velocity with the Earth. And a geostationary orbit, it is a geosynchronous with a zero inclination. It has a zero inclination angle, and again, it's consisting of a zero eccentricity. The satellites remain the fixed from above point on the equator for geostationary satellite, and these orbits are classified by the longitude of their satellite point on the equator. We know that the Earth is always rotating around the sun, and it's a constant angular rate. It has a constant angular rate. Satellite has to move. It's maintain constant speed in one orbit. That's around 24 hours period, and the altitude it's maintaining 35,850 kilometers. As per that, it is moving. Next one, it is a sun synchronous orbit. The sun synchronous orbit is a special case, and the satellite which travels from the north pole to the southern pole, and again it's a turn towards eastward. In a sun synchronous orbit, the satellite passes over the same part of the Earth, roughly is the same local time it's maintaining in a day. Suppose when we think of orbit, passing over the poles, the Earth rotates under its every 24 hours, so that any point of the surface it will pass below the orbit of every 12 hours. Please wait 1 minute. Yeah, sorry for your interruption. I don't know why someone is scratching on a screen. Okay. Yeah, satellite tracking. The satellite tracking it involves the pointing an antenna. And based on the antenna, it is moving and it's located on the ground, and it's following the position. And again, it's depend on their latitude and the longitude of antenna. The it's showing the recording values and the same, and it is possible to calculate the elevation of the angle. Yes, definitely. With using of this data, we have a chance to calculate the elevation angle, and again we have a chance to measure the azimuth angle also, where it is locating and what is track location and how much angle it's angle, and the same angulation we can have a chance to measure. And suppose if you see the calculation and observation of the position of a satellite, which are compared to improve the knowledge of forces and acting as a satellite, we see the errors, we rectify the errors, the errors how we are getting and how we can rectify the same errors with using of a ranges that is 10 centimeters to 10 centimeters to approximately 2 meters. Yeah, this is a satellite tracking. You see here, and suppose maybe if it is a horizontal position that will be moving. If it is moving like this, and the elevation it's measuring here, the elevation angle we can measure, and it's indicating the azimuth. It's a perpendicular, almost it is equivalent to the uh, eastern part. Then if it is moving towards of a north, it is moving towards of a north, and we can measure the azimuth angle from here to here. Okay, now introducing the rockets. Yeah, it was in first the rocket word. It was introduced by the Tipu Sultan against the uh, British emperors. It was made a long bamboo stick with using of a 2 kg gunpowder, and it's a gunpowder and the rocket and the swords it is having. Then the each rocket is having the weight approximately that is 3.5 kg, and travel approximately it is a 1.5 kilometers distance from where it was started. Yes, it has observed it has a outstanding performance, and at the same time, multiple rockets were fired on the British cavalries, and that was a Tipu Sultan's rocket. It was displayed in a artillery museum in Woolwich, in London. Now we have Wait. Yes. Now we have a history from 4 decades onwards. We have an history to launching the different satellites or rockets. Those we'll see. In firstly, actually, in 1963, it was begun in the St. Mary's Magdalena Church at Tumba, and again the church it was built in 1962. This is the location what it is showing here, and again from 1988 onwards, it was showing as a museum. The first launching was done here, Apache on 21st in 1963. And okay, before going to discussing about this one, just I would like to tell you the Indian remote sensing program. The Indian Space Research Organization was set up in 1969, and it was a developed organization. And again, it is controlled by the Indian Department of Space, and it was located in Bangalore. And also, it is operating the related facilities as providing in Vikram Sarabhai Space Center and Srihari Kota Space Center, ISRO Satellite Space Center, LPSC, that is called as a Liquid Propulsion System Center, and again yeah, and the Liquid Propulsion System Center and the Space Application Center and ISRO. It will also working under the same department, that is the Indian Space Research Organization. ISRO telemetry and command tracking networking system, that is called as a ISTRAC, and these all will be working under the guidance of Vikram Sarabhai, the father of Indian space development. And the main aim of our Indian space it has to be developed as a Indian space development. It is to achieve the economic progress, and it has quickly and actively started the tackling the several programs, and again. And again, it is solving the different problems. Indian remote sensing program, and we have started the launching the satellites from 1979 onwards. The first one, it was launched June 7, 1979, launching vehicle. We have used the USSR launching vehicle that is called as a Intercosmos, and second one, it is Bhaskara 2. It was launched in 1981 in the month of November 20, and there also we have used as a experimental, and we have used to launch the vehicle by the USSR, that is also Intercosmos. Next one, it is the IRS series was started. Indian remote sensing satellite system was started. That's the first. It was IRS 1A. It was launched on March 17 in 1988. The same USSR launching vehicle we have used, that is Vostok. We have used the Vostok, and again we have used various types of Indian remote sensing satellites, and again, yeah, the IRS 1A, it's carried two sensors. One, the one it is this one, it's having the 72.5 meter resolution, and second one it is the LIS 2. LIS means it is speaking about linear image self-scanning system. Linear image self-scanning system, it is called as shortly we are calling that is as a LIS 1. And again, LIS 1, LIS 1, that means IRS 1A. It was retired from his services, and it was collected around 3 lakhs of images. And again, immediately our government launched the next one, IRS 1B. That was launched in 1991. Again, we have used the launching vehicle. That's Russia Vostok again. And again, after that, Indian space program. Indian space program, it was introduced. Based on this, we have again to launching the satellites. Here in 1983, sorry, in 1981, the first Apple was experimented, and we have used that launcher that was from France. It is called as Aryan. The Apple one, it's called as a Aryan passenger payload experiment. It was launched on 19th June 1981 from Kourou. The weight was approximately 670 kgs, and it is geostationary. And the equator, it's an angle at 102 degrees in the east. It was the first Indian indigenous geotest communication satellite, and it was launched with Meto satellite. And second one, it is Indian TV programs. It was educational purpose, educational satellite we used, and educational teleconference were relayed. And again, the Apple was deactivated on September 1983. And next one, it is Aryabhatta. And here we used the launcher name SL8. That's from Russia again. The launch, it was launched on 19th April 1975. And it was launched from Kapustian Air. The weight around 360 kgs. And the perigee apogee was 563 into 916 kilometers square it has. And the satellite was named after a 5th century astronomer and mathematician. And it was designed for 6 months of X-ray astronomy, and it was controlled and handed over to the Indian scientist on the 3rd day. But Indian designed the transformer, it was a fail. Only one day it was used, and again finally it was a fail. Yeah, actually the next slide here. Let's see. It's launching of vehicles. I'll tell you later about this one. And again, Bhaskara 1 we used. Yeah, Bhaskara 1, it's related to the Indian remote sensing program. And here we used in Bhaskara 1 and Bhaskara 2. We used the launcher up from Russian, and one it was in 1979, and one more Bhaskara 2, it was launched in 1981. Bhaskara 2, the weight it has approximately 444 kg, and the orbit swap it is around 541 into 557 kilometers, and it is useful for television images, and it's capturing our Indian subcontinent images. Okay, there are various types of satellites and different types of vehicles we were used, and after that now we have our own capability to using, and again we are ready to start we are using our own launching vehicles. Then we have started, that is Indian satellite series. Indian satellite series up to 2001 we have used Indian remote sensing satellites, and one it is related to the polar satellite launching vehicle, and one more it is GSLV, that is geostationary launching vehicles we used. After Bhaskara 2, again we have used Rohini 1B, Rohini 2, Rohini 3, SRAS, and different satellites we were launched. And from that, slowly we have developed our own system. And Indian satellite, it was introduced in 1982. It was launched in 1982 on 10th April from Cape Canaveral. It was launched from USA. The weight approximately it is 1,152 kgs, and it's useful for geotel communications, and it's a meteorologic satellite. That means the meteorological information we'll get from this one. And we every 30 minutes it is releasing the data. about the meteorological information. Yeah. And next one, it is an Indian satellite 1B. The Indian satellite 1B, INSAT 1B we are calling, that is, it was launched in 1983 in August 30th. And then again, it was launched from Cape Canaveral, and the weight around the same 1152 kgs. And its video recordings have suggested that it might have been struck by orbital debris during the releasing the data, and through this could not be confirmed. And it was controlled by the Hassan master. And again, it is reinstalled and restationed at 74 degrees in the east place of the or beside of INSAT 1A. And after that, that means it was working partially. Then after the full operation, it was achieved in October of 1983. After 2 months, again, it is going to be started to work. Around 36,000 of Earth images were sent from this one. And again, different types of satellites we have launched. And again, in 2005, ISRO Polar Satellite Launch Vehicle, that's a PSLV C6, successfully we have launched the Cartosat 1 and Hamsat satellite from Sriharikota. That was in 2005. And again, before that, 2003 and 2004, the first operational flight GSLV, Geostationary Satellite Launch Vehicle, and it was successfully launched EDSAT from Sriharikota. Yeah, in 2003, again, we have used the PSLV. That's a PSLV C5, and successfully it was launched Resource Sat from same as Sriharikota. It was in 2003. Yes. The Indian National Satellite System, it was established in 1983 with commissioning of INSAT B. That means when we were launched, that's the INSAT B, Indian National Satellite System. And again, it's a joint of Department of Space, inclusion of Department of Telecommunication. And again, it's a collaboration with Indian Meteorological Department. These are all the departments collaborated and established in 1983. They were worked together, and they're all the responsible. They're all means here, they will be all working under the Department of Space and Technology. And it is a responsible for establishment of operation INSAT space segment. And again, INSAT 2D, INSAT 2E, ISRO, and ISRO, it was released. It's released the 36 megahertz of energies of units, and it's equivalent to the C-band capacity. We have some ABC bands. I'll tell you later. That is what about those bands. Yeah. Now coming to the satellite system parameters. Yeah, just you see here, yes, so it was launched with different vehicles, and in August 79 or July 80, between that gap, the first one it is a satellite launching vehicle, and you see the height in a meters, approximately it's contained at 22 meters, and payload, the amount it is weight, it's a 40 kgs, and it should be the orbit it's located, and it's based on the low Earth orbiter system. And next, ASLV was introduced, and followed by the PSLV, GSLV, and GSLV MK third. It's advanced. You see here the development of technology to launching the different vehicles. Yeah, from 1960s and 70s. Here, it's a basic technology, and it's using the avionics and aerodynamics. The material, maybe it's a liquid propulsion, and the other structures will be using. And then second stage. The second stage is in 1980s. In 1980s, we used liquid propulsion, and it has a large booster. At the same time, consisting of a large upper stage. Later onwards, in 1990s, the cryogenic engines were introduced. That means the cryogenic technology was introduced. You see here this one in 1990s. Then in 2000, from there onwards, we have used heavy cryogenic engines, and which are having the large boosters. And again, we have a 2 launch pads also. The configuration or the satellite bus station system. The satellite hardware, we are calling that the satellite hardware also. A satellite system, it is made up of different equipments, and it has different machines. The main aim it is will give the job to the satellite, and must ensure the satellite it should be reach the goal, and as per that the equipments will be arranged. What's the purpose main? For example, this machine's equipment is including to observation of Earth sensors. That means the Earth observation satellites, and which are providing the communication system or communication information, and it's giving the information of landforms in the formation of different images. And the bus system, it's consisting of many subsystems like telemetry tracking and commanding system, and electrical power system also it has, an automatically altitude control system, and it has a propulsion system, structural system, and terminal control system. Okay, if we go internal structure of this one, the gross weight maybe it's consisting of 294 tons, and the height maybe it is 44 meters. The diameter maybe around it's a 2.8, and heat shield it's a 3.2 meters, and it has a 4-stage vehicle. Then again, if you see the internal structure of the same in PSLV, it is categorized as A, B, C, D, and A, B, C. Just you can see it is A. Again, it's divided into the this chamber. It is divided into the 5 parts. One, it's a payload. It has here in this chamber, and heat shield will be also there. Payload adapter. It's internally it was arranged. Equipment bay. And fifth one, it is an auxiliary payload. You see a different colors, it was mentioned. The red color, it's a control. It's indicating the control and guidance system. And green color, it is related to the propulsion subsystems. Next one, B section. In a B, it's indicating the 4th stage tank here, the final one. One by one, it is when it is traveling in a track or along the track or in the orbit, one by one, automatically it is going to be removed, and only the main frame it will be working. Yeah. In a B, it has a 4th stage tank, and again along with that one, 4th stage engine will be also arranged here. And it has antenna also. Yeah, in a C section, again, it's consisting of antenna. It's inside. Antenna, it has a sensors. The sensors will be absorb the features and absorbing the radiation. Either maybe it is a passive radiation or active radiation, whatever it is absorbing by this one. And next one, it is it's a reaction thruster. A reaction thruster, it will be reacting for any sensitive element will be observed by these sensors. Immediately, it is getting the respondent. And 10th one is a interstage, and 11th one is a 3rd stage adapter. Yeah, in a B, it is a 4th stage adapter, and in a C, 3rd stage adapter nearby this one. It was arranged here. And D category. The 3rd stage motor, it has a 3rd stage motor. And it is having a control, flex nozzle control. The fuel, whatever it is burning, and it will be released from this is a nozzle. Yeah, from here onwards, 14 and 15. It's an interstage, 14 and 15 interstage of lower and upper. Yeah, 16 is a 2nd stage tank. This one, 2nd stage tank. This area. And 17 interstage of upper unit. One, it is the 2nd stage retros. One somewhere here. Yeah, it was missed somewhere. Some area. And 19th, it is a Ullage rocket. 20th, it has a control. It is called as a gimbal control. 21, again, second stage of interstage. I mean, in a second stage, it has a interstage, lower interstage. In 17, it is upper interstage, and 22, it is a second stage. In sorry, 21, it is an interstage of second stage engine, and 23, it's a first stage of the retro. That means slowly, stage by stage, they are going to be moved, and they will be splitted. And 24th, it's a first stage motor. From here to here, it is a first stage, and second, third, and it's a fourth. 25th and 27th. It's an injector tank. 26th, it's a strap on a motor, the side one. 28, it's a core base shroud. 28, it was nearby the base. It was fixed nearby the base. 29 is the roll control engine. It's rotating and it's supplying the energy. It's required very huge energy. It has a escaping nature, escaping velocity, astronautical velocity it has, and then only it's a move on a track with a particular location. This is a commercial phase of PSLV for different countries. See here, Cartosat 2 or IMS 1. It belongs to the our Indian nation, and CAN X2. It belongs from Canada, and RSAT 2. It's a Denmark, and Qt 1.7. It's from Japan. NLS5 and CAN X6. It belongs to the Canada. And this one is a Compass 1. First launched by the Germany. And again from Japan, seeds. And here Delphi C3. It's from Netherlands. The final one, it is from Germany, Rubin 8. These are all various types of satellites. You see the structure. Indian meteorological or metro satellite. And this instrument, this is a Rubin 8. It was imported from Germany. Same again, GSLV configuration. And it's also having these stages. It has 3 stages, GS1, GS2, GS3. Yeah, this is. The satellite, it was fixed in the edge of or nearby the payload. It's a payload adapter. You see, it was fixed here. And by stage, they will be removed, or stage by stage, they will be separated from the solid motor. You see, it's a solid motor. Actually, it's all the liquid strap jaws will be fixed along the solid motor, and when it's traveling on the track or orbit along the orbit, they will be separated and they will be removed. And finally, it is a settle down in a track, and it's rotating throughout the earth. You see this one. This is the sequence, how it is going to be switched, or how it is going to be moving along the track. And it's maintaining some speed with the height. Speed with the height. When it is the ignition stage, and it's moving in a 110 seconds, the height it's reached around 36.8 kilometers from here. This one. In second stage, you see here it's splitting. Once it's reached somewhere height, approximately it's 100 kilometers, and then it's going to be separated. As per the height, it is going to be separated nearby the 67 kilometers of a height. It is separated. As per this track, along this track, it's traveling. And finally, it's reached the final shell. It is also removed from this one. And again, it's separated, and somewhere it is located, and it's moving around the earth. Yeah, this is indigenous cryo-stage development detail. You see, this is a machinery, how it is look like. And this is a part of Chandrayaan-1 when it was launched by the PSLV. Again, this is about Chandrayaan-1 payloads. So no need to you, only just knowledge purpose I'm showing you. These are all the signatures and different marks on a moon. It's about a GSLV system. And it's speaking about to reach moon by human and how they will become a return. It's a long-term perspective. It's a low Earth arbitrary related. And here the GSLV MK2 can be used to carry the Q4 to 6, demonstrating it's a heavy lift launch vehicle engines, these two, and the height it is different, you can see here. And at the same time, velocity it is also different. Yeah. It's based on the lunar circular orbit. These will be moved based on a lunar circular orbit. You know, it's the vision of a 2025. In 2009, we have used the indigenous cryogenic upper stage. In 2010, geosynchronous launch vehicle MK. In 2015, semi-cryogenic engines were introduced, and the Indian human space mission was started. And again, reusable launch vehicle it was introduced in 2016. And again, the cryogenic engine, fully cryogenic engine. Previously, it was used semi-cryogenic or partial cryogenic engines were used. In 2017, we are used fully cryogenic engines. In 2018, interplanetary missions were introduced. And again, 2020, advanced propulsion for planetary exploration. In 2020, we are using the two-stage to orbit, reduce the cost. Previously, we have a four stages. Four stages. Here, four stages. One, it was clicked here and moved. Second one, third one, fourth one. Four stages we have used. Now we are using the two stages. Okay, what's the use of these are all the satellites? It's useful for to getting the data, the first one. The main thing it is to getting the data and to develop the communications and how we will get the data. How we will get the data? We'll acquire and we'll get the data with using of sensors. I told you in previous classes about sensors. We have two types of sensors. One, it is passive sensors, and second one, it is active sensor. And based on remote sensing, the sensors, how they will getting and how they are releasing the data. Data means maps. And the main objective of this one, in the presence of a positive sensors, the data, how it is will be releasing and how the energy is a reflection and re-emitted. And again, it's speaking about the importance of the platforms and ground-based sensors, and how we can define these passive and active sensors. Yeah, before going to that discussion part, we have to know about the some instrumental parameters. To take any image and which can be released from the remote sensing technique and it's released and used by the remote sensing technique, and the information it is going to be carried by the electromagnetic radiation, and it should be maintained the particular wavelength frequencies, and again it should be a transparency. Suppose the atmospheric limits the possible wavelength ranges about around 0.4 to 15 micrometers, and this area it will become under the infrared and visible ranges. And again, maybe if it is increased up to 1 millimeter to the 1 meter microwave region, and it's containing the gigahertz, the frequency range, maybe it is a 3 to 300 to 0.3 gigahertz, and the visible and infrared regions is conveniently subdivided into the near infrared and naturally the occurring radiation from the Earth's surface. It is found in all the ranges of a wavelength. Either maybe it is a visible range, or maybe it is a nearer by the infrared ranges. Yes, we know that the sun is providing the sun source. Sources of energy. The sun it is a major source for energy. Either maybe when we are using the artificial or natural. So particularly when you come into the remote sensing point of view, will depend on sun resources or sun energies. The sun energy may be either it is a reflected or sometimes maybe not. Depend on the visible wavelength range that should be happened. Absorbed and remitted. It's a common factor. It's a common thing. It's a common factor and it's a common thing in a remote sensing. Or sometimes maybe it is absorbed by the different objects when it is re-emitted. That will be possible. The remote sensing system which measures the energy that is naturally, it's available naturally. It is called as a passive sensor. That means the natural energy, how they will release the natural energy, it is releasing from the sun rays, or it's available by the sun source. So such type of natural resource or natural energy, it is called as a passive energy. And the sensors are calling as a passive sensors. And again, the second one it is, suppose if it is not reflecting and it is not naturally formed, or maybe it is not naturally not reflecting. And the energy that is naturally it is emitted, whatever energy, if it is a fall on object, the object will absorb a little amount and main amount it is reflecting. So such means here artificially the energy if it is released. Artificially the energy if it is released, that is called as a active sensor. The sensors which are emits the radiation and it's directed towards a target of a area. Either maybe it is a passive sensor or maybe it is the active sensor. But our focus it is, that means our main focus it is on objective. The reflective and emission properties are different in a different material, and it should be orientation of the electrical field vector in the electromagnetic radiation. The sensors which are used to collect and record the energy, and it is reflected or emitted from the target of surface. It must be reside on a stable platform, and it can be removed from the target of surface area. The passive sensors and the active sensors, the passive sensors are non-scanning, and it is a non-imaging rays. Again, it's consisting of a microwave radiometer or a microwave radiation of energy and magnetometer sensors, gravitometer sensors. Along with that one, Fourier spectrometer sensors will be also available, and it's these kind sensors it's having the cameras, and the camera it's consisting of a monochrome. It's detecting for a different colors and natural color, infrared color, and others. And if you see the active sensors, in active sensors, it's a non-scanning and non-imaging. And again, it has a non-imaging and non-imaging and scanning imaging. In a scanning imaging, image, it can be scanned by the image plane, and it is an object plane scanning. In a passive phased array radar, it is fixed with this one, and it is useful for image plane scanning purpose. And one more, it is an object plane scanning. It is a RAR. It is called as a RAR. That's a real aperture radar. And object plane scanning. It is synthetic aperture radar. Yeah, I'm stopping here. We'll see in the next class. Okay, I'm stopping.